Yeah, since the computer online, and we got the old fashioned.
Yeah.
Hey, welcome back. We'll continue now with the second lecture today. This is Sergey Syritsyn. This is first of two lectures in Lattice QCD. So let's see, we're recording and it's all good. So Sergey, thank you.
Microphone or anything?
It picks up.
All right, welcome to the second lecture of today. So I'm a professor here at Stony Brook, and I'll be around for the rest of the week. So if you have questions after these lectures, I'll be happy to join you in the discussions during coffee breaks, explain if you have anything specific. So I'm going to tell about Lattice QCD. So this is mostly theory talk, and I will in the second half tomorrow, I will talk a lot about things that Lattice QCD has done and can do and will do. But today's it's mostly formal. So I'm sure everybody heard about Lattice QCD already, and this is one of the most, if not the most important theoretical tools we have to, well, basically make QCD work, right? So we know that QCD is the right theory beyond any doubt, but the problem with QCD is that we don't really know how to work with it at lower energies, close to the nuclear physics, right? Hadrons, it kind of becomes difficult. So today's plan is I'm going to show first over the successes of QCD and well, that sort of introduction of what QCD can do. Summary of the last, not the summary even, just highlights of the last decade or so, or 2 decades, and then I will describe how the method actually works and what it's founded on and what the small details that are important to make it work, what the algorithms are. And this is, of course, a very basic level introduction because it's impossible to cover this in an hour. Well, so the second day, we'll see how it goes today. Maybe I'll dig into that a little today as well. I will discuss various things that Lattice QCD has been able to accomplish and what the plan is for the future. All right, so why do we even need Lattice QCD calculations? So you know that QCD is known for the strong coupling, right? So towards the lower energy scale, about 1 GeV, it explodes into Landau pole or becomes highly non-perturbative. You have order 1 lattice QCD, lattice QCD coupling, a strong coupling, and perturbation theory works only on the other end, where you have order of Z boson mass, then it works fine, more or less. And anywhere in between, you have multiple orders of perturbation theory that you need to make it work to match things on the quark mass boundary and so on and so forth. But if you're really talking about hadrons, right, about the hadron spectrum, interaction of something like nucleon-pion scattering or the structure of the nucleon or pion itself, then it is impossible to do with perturbative physics. You need some other methods. So QCD is also a very special kind of theory, right? It has a number of unique features. It has a dynamically generated masses. So as you know, most of the nucleon mass, for example, comes from the gluon energy, whether it's just, you can call it the kinetic energy of quarks or some kind of interaction energy of quarks and gluons, or it's a gluonic, basically, energy density. And the fact is that the quark masses, the bare quark masses, which is itself is a bit of a flimsy notion, they contribute about 1% of the proton nucleon mass. Also, QCD has this wonderful feature of a broken vacuum state. It has a vacuum condensate of quark, basically quark scalar density, right? And that gives rise to the interaction carriers, to the mesons that are carriers of strong interaction. The fact of the spontaneous chiral symmetry breaking in itself has, well, we don't know how it works. And the same topic, right? We don't know how exactly the flux tube forms in QCD. So if you have quark and antiquark, you pull them apart, you have this kind of spatially extended quantum pure state of gluons that comprise this heavy object that has energy growing with the length. So if you look at the QCD at multiple scales, right? So at the low energy, you have these bound states of quarks and gluons. If you look a little deeper, there are strongly interacting quarks and gluons. And if you go higher in energy, then basically becomes free quarks and gluons. And that tells us the possible recipe to study QCD is that, well, we want to look at we have to make separation of scales, right? So lattice, essentially what it's doing, it's large volume that is capable of fitting multiple hadrons in it, but at the discretization step, lattice spacing, it's not free, but it's something that is you can write a Lagrangian for. And the questions that lattice QCD is trying to work on is, well, it's what is the spectrum of hadrons? What are their interactions? What are the structure? Some, for example, spin contributions and the mass contributions, and how the quark and gluon carry momentum inside hadrons, particularly nucleon. Other questions are in particle physics, for example, what is the sensitivity of our probes, such as the dark matter detectors, how sensitive they are to dark matter, right? So how sensitive are they to symmetry breaking? Still, the question which has not been resolved is what is the exact mechanism of confinement, how these strings form, and what keeps the quarks inside nucleon hadron together. So, all right, so let's go right there. In little history, it started about 5 decades ago. Ken Wilson formulated QCD on a 4-dimensional lattice. And that, of course, at that time, there really was no compute to speak of, right? So you basically had your maybe calculator or something like that. And the main reason for introducing lattice was to regulate the theory. So, you know, quantum field theory doesn't really have meaning without a way to regulate that, to cut off high momenta in the fields. It's the very important feature of lattice regularization is that it preserves gauge invariance. So if you've taken quantum field theory courses, you know gauge invariance is very important. It helps us actually renormalize the theory, right? But how you do this in the perturbation theory is always a little, you have to do you have to be careful about this. So in lattice, as we will see, this construction of a regulator is explicitly gauge invariant. So right from the start, we preserve the most important symmetry of the theory. And the problem, of course, back 5 decades ago, there was no way to do any calculations except maybe try to do some perturbation theory on the lattice, which you can imagine is quite cumbersome because space rotational symmetry is broken. Translational symmetry is somewhat broken. But within the 5 decades, right, developing theory, algorithms, and probably equally important, the computing power, we have the wonderful method to calculate from the first principles, just from the Lagrangian, we can go to the properties of hadrons. And that has been a wonderful success. And the horizon is just expanding of the things we can do. The goal is to calculate all these hadron parameters with the full control of systematic uncertainties, and that will just improve as we go on. And it's possible to do that. So there are no model uncertainties. This is first principle calculation. So basically we want to simulate QCD, do QCD calculations within a box of about 5 Fermi size, so that a few pion Compton wavelengths fit in. We are not really feeling the boundaries of the box. And at the same time, the UV cutoff or utilization scale is about 1 to 4 GeV, practically speaking. So the inverse lattice spacing, that's what's lattice QCD scale. And we don't want to go below that scale, not because the coupling explodes, but because there are discretization errors. So it's just difficult to discretize the action and discretize the observables that you try to calculate. And also, a third reason for this kind of scale, well, obviously, the finer the lattice spacing, it becomes more expensive. The question is, why cannot we simulate, do calculations with the coarse lattices? One additional important reason is that we want to make sure we can connect to perturbation theory. So we, for example, calculate, I don't know, like tensor charge or axial charge, and we want to make sure we can renormalize this to something that makes sense in perturbation theory. So currently, the Lattice QCD is a huge community. It's an annual conference, about 500 attendance. There's a open community software data sets. There is a report published every 2 years with the summaries of nucleon kind of and the meson properties and their interactions. It's a well-coordinated process, so which is a signature of a mature community. And more recently, we started as a community doing synergies with terminology. For example, extracting PDFs from experiments is, as you know, is tricky. Well, PDFs maybe not, but something like TMDs and GPDs, they require additional input from theory, and that's where Lattice fits in very well, as we will talk about that tomorrow. All right, so let's just look at a couple things that Lattice QCD was particularly successful in. So 2008 was sort of a landmark, remarkable year for Lattice because it was the first realistic calculation of hadron masses. So there are points here that the red points are predictions, the blue points are inputs. So you need to fix the parameters, of course, the Lagrangian. So you cannot just generate everything from nothing. But the prediction of KN mass, nucleon, and other baryons and mesons were spot on. And that, of course, with some error bar. So within 5 years, there was an improvement on that. The calculation on the left was done with what we call SU2 symmetric flavor, which means that light UND quarks had the same mass. And after that, and also no electromagnetic corrections, just QCD itself. And of course, next order of importance is including the isospin breaking, the difference between light and between up and down quarks, and also electromagnetic corrections, and they were also spot on, which of course very reassuring. So currently the predictions for the masses of various hadrons are also spot on, and also there are some, for example, the PC star, it's not experimentally known, but there is a Lattice value for this. So Lattice in some sense may be ahead of experiments, which is a good thing. Okay, so all right, another couple of examples. For example, neutron decay, neutron lifetime, right? So very well-known quantity, extremely important for setting the scale of the weak interactions. But it has a couple of unknown things from scratch, right? So we don't know what the VUD matrix element of CKM matrix is. Well, we know it's close to 1, but we don't know precise value. And also the axial charge we have to extract from elsewhere. So there was a big puzzle in Lattice for a long time with how to calculate the axial charge. And so basically this is a matrix element of the axial currents between neutron and a proton, to which the W boson attaches to, which then decays into neutrino and electron. And turns out that this is a particularly difficult quantity for Lattice because there are excited states in it. For example, nucleon pi state contributes a lot. So there was a lot of work done. And about 2018, there was a calculation, which, of course, still it's the Lattice result here has wider uncertainty than experiment. But all the community, as the community converges to the same value, everybody confirms the same result. And currently, this what we call the flag average, or the review that published every 2 years. The value is commonly accepted it's still below. The precision is less than experimental, but at least the value is very close to the one which is known from experiment. So another success, and another thing to mention here is that the nucleon structure itself, right? We can look at the nucleon structure in many different ways. One, the most basic one, is to look at the charge and magnetization, which of course is, the spatial distribution converted to the Fourier space is called form factors, right? So there is a form factor for the electric charge density and the magnetic charge density inside a nucleon. And so there's difficulty in these form factors. You cannot really resolve the spatial distribution less than the wavelength of the interacting photon, right? So it's a bit of a the form factors is a bit of it's a Lorentz covariant thing, but they are related to charge and magnetization distribution with some big caveats. All right, so you can think about that, these form factors as the Fourier images of the electric and magnetic current, electric charge magnetic current, Fourier transformed in a bright frame. So if there's 4 form factors, electric, magnetic, and the proton and neutron. And the black points, which are kind of hard to see here, are the experiments. You can see lots of black points in the small neutron electric dipole, electric form factor. So it's itself is electrically neutral, of course, right? So if you start having some kind of momentum in the electron coupling, in the photon coupling to the electric charge, then, well, it's non-zero, it's positive, which is normally interpreted as the neutron has this core and the surrounding of different sign charge. So lattice results approach to experiments in this particular quantity in precision. So the colored points are the lattice results, and the black points are experiments. So the experiments on the other form factors, which are order 1, are expressed with these phonological fits, basically these black dash dotted lines, and the lattice is right on top of the experimental values. Another important thing is the forward limit of the magnetic form factor, which basically gives you the magnetic moment. All right, so these are just 4 examples of how lattice QCD has been able to reproduce features of the nucleon. So now let's go ahead and figure out how it all works. So we want to start from the Lagrangian, right, which is just just the Young-Mills plus the fermions, right, and interaction. So quarks interact with the gluons with a strong coupling. And starting from this Lagrangian, directly we want to determine the hadron spectrum structure theory for nuclear forces at the low energy, or otherwise known as chiral perturbation theory, another important thing. And also whatever is necessary for the particle physics to put constraints on whatever new physics we want to find. We want to control the systematic uncertainties, which we'll discuss at the end today. So it will be gauge invariant by construction. There are important symmetries we want to preserve. So there is a Lorentz symmetry and the chiral symmetry between left and right-handed quarks. So the quarks have very small current mass, right? So left and right parts of the Dirac fermion talk to each other via the Dirac mass, and this mass is small. So basically, left and right are almost independent species. But on a lattice, it's not easy thing to preserve. So we want to make a lattice spacing small and volume large, and set all parameters to the physical values. Eventually, we want to introduce corrections from the electromagnetism and from isospin breaking. We want to incorporate in some way other particles. For example, if you have effects of electroweak interaction with the exchange of W bosons or neutrinos, you want to put them on the lattice in some way. So neutrinos are particularly difficult because they're massless, right? And you have some kind of neutrino exchange in the process, then you have to add it in some other way. So, for example, neutrinos participate in the so-called long-range kind of interaction, and I will talk about this tomorrow in the review of the. It's important for neutrino-less double beta decay. All right, so I presume everybody's familiar with the path integral formulation of the quantum field theory. Just a quick reminder: we can take quantum mechanics and convert it into path integral, right? So if you have a single particle, which is normally described by a Schrödinger equation, you might literally rewrite this as a path integral, where your amplitude going from point x1 to xn at time t1 to time tn, right? You can write this as integration. This amplitude can be written as integral over all intermediate time instances, right? With the coordinates, you integrate over all coordinates with a specific kernel. And what is wonderful is that this kernel can be expressed just using the classical Lagrangian. So this is how we currently do quantum mechanics. In quantum field theory, it's much more convenient to do that using path integration because it's basically it's Lorentz covariance, right? And you start from the Lagrangian, you don't have to mess with the second quantization. So it makes a lot of sense. And this is the primary way we want to do this on the lattice as well. So, or in any quantum field theory, right? So we want to integrate over gauge boson field, over fermion fields using with the weights, which is complex phase with a classical action, right? And whatever observable we want to calculate, typically we calculate correlators of fields. So we can put in this always stand in for example, nucleon creation operator, nucleon annihilation operator. And we want to take this integral over fields at each spatial time point. So this is a formal expression. And to make use of that, we need to make a few steps, which I will go over. And so first we need to convert the 3+1 dimensional Minkowski space in the Euclidean space. Then we need to discretize the fields in action on the 4-dimensional lattice or grid, right? The important step is to, the actual algorithm, right? To how to take this integral. And that is done with the Monte Carlo integration, exploring the configuration space of fields. And the fourth is, basically evaluate what we need to evaluate. For example, correlation functions from which we extract the masses and the matrix elements. All right, so converting from Minkowski to Euclidean space, this is otherwise known as Wick rotation, right? You make the time imaginary, and this turns this hyperbolic surfaces of Minkowski space basically into circles, and everything is essentially a space-like. So you lose future and past in our usual sense. All the particles become virtual. All separations are space-like. But the big upside is that the space is now all four symmetric, right? So it's fully rotationally symmetric between space and time. So if I attempted to discretize the fields and on this kind of space where they have null surfaces, right? And the invariant measure is the interval. That would be much more difficult just from a practical point of view. But much more important thing about this Wick rotation is that the action exponential of the action turns from the oscillating complex phase into a real valued probability. At least if this Euclidean Lagrangian is real valued, right? So there are cases where you, by doing this by going from Minkowski to Euclidean space, you actually generate complex contributions to the Lagrangian. Those are cases where you have sign problem. So this is a separate thing. We don't encounter that in currently what we do, and we don't know how to get around this. So we will just assume that the Lagrangian we get here is real valued. So a simple example, of course, is a scalar field theory. You start with this derivatives of the field and the potential, right? So you convert that into Euclidean space. The potential term basically changes sign, right? So you have time derivative, kinetic term, and the potential. And the state evolution turns from a complex oscillation with the energy into sort of Euclidean time decay. The particle decays with the energy. If it's zero momentum, it's just a mass, right? And the same happens to the correlators. So if we calculate somehow the correlator of these fields using our Euclidean field theory, then we can look at this, extract the exponential, and find the mass of the state. So the downsides, of course, is that you're not really working with a real time. So you cannot calculate any real time dependent processes. And in particular, you cannot do scattering directly. So if you have two particles, the normal way we treat this in quantum field theory, we have asymptotic states at minus infinity time, infinite past, right? And then they interact, and then they go to infinite future. And these limits, they're not interacting, they're separated by large distances. So they're essentially free particles. It does not happen on the lattice. So all particles do, you create them and they kind of decay in the imaginary time. But you can extract the spectra and you can extract the matrix elements from the correlation functions. And turns out you can also extract the scattering. but you have to do this by the energy shift because you put the two particles now, right, into a box. They are kind of forced upon each other, and their energy of interaction shifts the total energy of the state. You can extract that. And then map this to a real scattering amplitude in Minkowski space. Okay, so the rest after that is very much similar to the standard Euclidean field theory, right? The way you do quantum field theory, you actually can do calculations in the Euclidean space using the standard methods, and then do the complex continuation back to Minkowski. In particular, we don't care working with the quark fields, with the fermion fields directly, so we can just integrate them out, right? So this is a normal Gaussian integral over Grassmann variables. It gives you a determinant of the Dirac operator. So this d slash is a standard differential d mu gamma mu kind of thing. And it has as many flavors, that as many factors you get of this determinant. So now you have this kind of probability, right? Which actually this determinant is real valued. Also the cases, so we can make it real valued using some constraints. After that, well, all we have to do is to calculate the correlators of, for example, of quarks. That'll give us a quark propagator, right? So the usual way we do this is the weight contraction that gives us, this has to be the inverse, t slash plus m inverse. And it has to be weighted with this weight exponential of the gluon action and the determinant of the all the quark species that we have. We usually have to work out weak contractions by hand and evaluate the average of this polynomial of the quark propagators to get, for example, nucleon correlator that has 3 valence quark at the creation operator and 3 valence quarks at annihilation. So we contract them and get a product of 3 quark propagators. The gauge field we have to integrate explicitly, but we do this numerically using Markov chain Monte Carlo algorithm. And there are two notable algorithms how this is done. One is suitable for local updates. Local means that if you change field at one point, then you can easily calculate the change in the action. And if you have non-local, then you have to be, well, more technical. You have to do what's called a hybrid Monte Carlo, which is similar to Langevin algorithm, but it's like integration over fictitious time. So the overall process, how this is done, you generate a sequence of these snapshots of the fields and enumerates these snapshots. So you update from n to n plus 1 to n plus 2 and so on, right? And then using each of these configurations, you calculate your observable, for example, a contraction of quark fields expressed as the polynomial in the quark propagators. And then you average overall your snapshots, right? And you get your, so it's, then it just goes as statistics where error bars will be suppressed as 1 over square root n. So there is a Monte Carlo kind of statistical uncertainty always present, and you can beat down on it with enough statistics usually. Depends on the observable. All right, so now let's go to the discretization of fields. So this is a bit of a technical detail, but I think it is very instructive to see how this is done. So again, starting with the simplest example of the scalar field, right? So if you have just scalar field at every side of the lattice, you can approximate the derivative in space and time by finite difference, right? Some overall directions, and you can then derive the free equation of motion. So we assume there's just a free scalar field with some mass, right? And then you can write find that the dispersion relation is very similar to the continuum one, except that you replace the momenta with the sign of momenta or the hyperbolic sign for the energy, right? Because the plane wave of a free scalar field would be something like this, plane wave in space and the exponential decay in time. And you can plot this in the within 1 billion zone, momenta from minus pi over a to plus pi over a, and you see it has a single pole, right? Single point in the momentum space where energy goes either to 0 if you have mass equal to 0 or to the lowest, which is the rest mass, right? So that's the usual way we treat these fields in the quantum field theory. Just work introducing the plane wave and see what kind of where you find the pole, right? Where the propagator turns into the denominator in the propagator turns into zero. So this is a sum of sine squares, but actually one of them is the hyperbolic sign with a minus for the energy. All right, so you have single species for the scalar field, which is great, but we don't have scalar fields in QCD, right? We have fermions, and if you try to do the same with fermions, and you do this in the simplest way, you just, well, do the finite difference for the derivative, right? And you find that the dispersion relation actually has two poles. So you have one pole where it's supposed to be at zero momentum, and then you have another pole, which basically is the same pole, right? It's because the Brillouin zone is, the momentum space is periodic with the Brillouin zone size. So you have another pole right here. And this might seem as just a mathematical curiosity, but in fact, this is a dynamical kind of thing. So this is introducing another small eigenvalue to the d slash plus m operator. So you remember when we had this integrated out fermion fields, we had these determinants, right? And the eigenvalues of this operator close to zero are what's determining basically the propagation of quarks. And these poles represent separate species. Physically speaking, these poles represent special species. So these points here are, you can say it's their sort of off shell, right? But the close to the momentum shell, it's what counts as species. And naive fermion discretization introduces this additional species, if you do it in the simplest way. And turns out there's no way around this. You have to introduce some other operator. So if you just have the simplest kind of toric periodic boundary condition for our box, you have this kind of doubling in each direction. So it's 2 to the power 4, 16 total species. And you can try to mess with the geometry of this momentum torus, right? So I'm figuring out maybe I can fix this with the boundary conditions. Turns out it's impossible to get rid of doublers. If you take this naive fermion discretization, you will always have at least one doubler in this topological kind of statement. And it has to do with with the differential geometry and topology. The number of left-handed species and the right-handed species will be always equal. And this is one-dimensional example here, or 1 plus 1, you can say. In this case, you have, let's say, one species moving to the right and another species, the doubler, moving to the left. If you extend this to 3 dimensions, then instead of left-handed, left moving and right moving, you will have left-handed chiral quark and right-handed chiral quark. So they will always cancel whatever chiral effects you might have or you might want to study. So if you want to introduce some kind of electroweak extension to the theory and write the Weinberg Salam theory on the lattice, you will not be able to write just the left-handed currents because they will always be accompanied by right-handed currents, right? And this will, for example, cancel the axial anomaly. So you will never have divergence of the axial current because the divisions of left-handed and right-handed will cancel. And this is kind of a bad thing. We know that the anomaly is important for the right dynamics of the field, right? So for example, such as a eta prime boson is the consequence of anomaly. And also the pi zero decay, right? That's governed by anomaly. So you want to have these chiral symmetry features. And in order to get that, you have to overcome the so-called no-go theorem, which was found in 81. So if you want to, and it says basically you cannot have everything, this list. So if you have regularized chiral fermions, chiral means you have only left or only right or not equal number of left and right, and you want to have them interacting with gauge field, you have to either sacrifice locality of the action or you will have doublers, and you have to do something with the doublers. So possible solutions are you can, for example, introduce additional terms into your action. So this is written here. I want you to pay attention to this expression. This is a formula for the what's so-called Wilson term. And this is basically a Laplacian term, right? So it would introduce momentum squared. This is similar to scalar theory term. It's a second order derivative. And it will fix the dispersion relation to have this kind of shape, similar to scalar theory. So you will effectively lift the doublers off the pole. You will eliminate those poles, and you'll only have one species. But the problem, of course, is that this kind of term you see explicitly couples right-handed and left-handed. So this kind of term breaks the chiral symmetry hard. And this fixes the problem at the expense of introducing another problem. You have large radiative correction to the mass, because if you also make these fermions interact with the gauge field, these derivatives will be covariant derivatives, and they will couple to gluons, and loops with these gluons will generate divergent contributions to the mass. So in order to get something that resembles realistic QCD, you would have to introduce negative mass to cancel that. It's similar to what you have to do with the Higgs mass in the standard model, right? We have to kind of subtract the mass, radiative corrections to the mass, and fine tune it. But this is inexpensive, numerically speaking, inexpensive correction to the Dirac operator, easy to implement, and it's most frequently used fermion action. So when you try to find some literature on lattice QCD calculations of what you're interested in, this is most likely you will see. So, or some modification of that. Usually it's discretization improvement. So you sort of add what's called a Clover term, and it improves the discretization to the next order, right? So the naive discretization is good only to order A, but the Clover improved is order A squared. So the practical, of course, implication is that you don't have to go to finer lattice spacing to get the same precision, and just extrapolate to continuum limit from coarser lattices. Another variant is so-called twisted mass fermions, which is basically introducing a term which is complex conjugate for up and down quarks, and that helps also with the discretization corrections. Another option to fix the problem of doublers, or sort of partially fix the doubler problem, is called staggered fermions. And it's been noticed that this naive discretization basically has the form in which there are 4 species that are decoupled from each other. So you can go down from 16 species to just 4. And this turns out it's good for simulating. It's, first of all, it's much more economical. It's much more efficient. And you can, for example, calculate this determinant contribution to the weight. And this is called this. So the determinant is normally called C-quarks. So the contribution of that can be simulated with the staggered fermions. But it's very difficult to construct, for example, nucleon operator from it. Not impossible, but much more cumbersome. And usually, frequently what people do, they have so-called staggered quarks as C-quarks, dynamical quarks, as they're also called. And then on top of that, there's a valence Wilson quarks. Makes it a very efficient computational scheme. All right, so what are the options to fix the chiral symmetry breaking? So you can fine-tune the mass, but what you cannot do, you cannot keep right-handed and left-handed fermions apart from each other. They will interact, and if you want to calculate some observables involving, for example, left-handed currents, it's very difficult to do with this kind of discretization. So it took many years to figure out the solution to this problem. And this is one of the most beautiful results, I would think, that came out of that. And it was initially, it was a fairly simple observation that if you go from continuum to lattice, you can imagine that as blocking fields, right? So after you go from continuum to lattice, you can sort of average the fermion fields inside a cube, for example, right? And when you do that, the usual chiral symmetry turns into what's called Ginsburg-Wilson relation. So your fermion operator Normally, in the continuum, it would anti-commute with the gamma 5, with this chiral gamma matrix, but on the lattice, you have this term appearing, which is quadratic in the fermion operator, and it vanishes if you go back to the continuum limit. But if you actually want to simulate chirally symmetric fields on the lattice in a consistent way, this is what chiral symmetry turns into. And if you do some algebra here, this kind of fermions which satisfy this relation called Ginzburg-Wilson fermions, you can find that the eigenvalues of this d slash, they actually live on a circle of this kind. And it's this kind of this structure of the spectrum separates effectively the physical species from the doublers. So here is an example of this operator, the d slash spectrum in the Euclid space. So the usual, the naive d slash turns out it's just a mass, which is the real parts, right? So it's shifted from 0 and then some imaginary momentum. And the physical species and the doubler sit right at the same point here. There is no way to discriminate between them. That's what we saw 2 slides back. And if you left the doubler species with the Wilson term, they are moved in they basically have this real valued divergent correction, right? So this is all expressed in lattice units. So you should divide this by lattice spacing if you want to have this in units of GeV, for example. So the physical species remain close to 0 and represent the physical pole, but all the other species are lifted. And if you instead of that, if you do the Ginzburg-Wilson, no matter what, right? No matter what kind of exact lattice formulation. So this tells you that the spectrum has to look like this, and you have physical species on one side, and all the doublers are collected on the other side. So what this does, effectively, it separates the physical species from doublers, and you can actually have a lattice version of the Atiyah-Zinger theorem, which says that D and D dagger must have different number of 0 modes. So if you think about that, on the lattice, you have a finite dimension, right? And if you have an operator and operator dagger, they will always have the same number of 0 modes, but this formulation actually moves the 0 modes, some of those 0 modes to the other side. So you can count only 0 modes here as physical, and that would reproduce the index of the operator, which is also has connections to topology and well. All right, so the solution, so this relation was known for a while, but the solution to this, how you actually implement them, was only found almost 2 decades later, and it's a highly non-linear kind of solution, and this is one of possible solutions, and basically this term essentially represents the argument of this picture around this M overlap. So if you put the center into this point, shifted away from 0, and calculate the argument of the spectrum in the center, you get the spectrum on the right. So this is what is actually used in the calculations where people want to have good chiral symmetry. But the problem, of course, it's very expensive. You can imagine evaluating this nonlinear version of the large operator. So this d slash, you can imagine this is basically a matrix which acts on vectors of lattice volume times spin times scalar, right? So it's a huge matrix. You never construct this matrix explicitly. You have to use some polynomial approximations to evaluate that operator. Another solution to this chirality problem was found a little bit earlier. It's called domain-wall fermions, and it works at the expense of introducing the 5th dimension. So we already have 4 space plus time, right? Space-time 4 dimensions, but then you sort of introduce the 5th dimension, and along this 5th dimension, left and right-handed modes separate. So it's known that in the 5 dimensions, there is no anomaly. So there is no problem with the anomaly, but what you do with this 5th dimension, you sort of introduce a defect, or you basically have a finite box in the 5th dimension, so that one-handedness, the right-handed modes stick to one wall and left-handed modes stick to the other wall, and then you also introduce a term of the interaction between them. So normally, you have to extend this four-dimensional lattice to a fifth dimension. So that introduces a factor of maybe like 20 or 30 or something like that. So this, you can imagine, this is order of magnitude at the very least more expensive than the usual fermions. And it was also shown algebraically, it's basically equivalent to overlap. So this all nicely ties back into the same theory of Ginzburg-Wilson fermions. All right, so in principle, to summarize, in principle, solution to chiral symmetry breaking on the lattice exists. It's expensive. It introduces a factor of 10 or more in the cost of simulation. So now, after all this, the only thing left to do is to discretize the gauge field. And after all this trouble, this almost quaint, right? The only thing we have to do is to make sure it's gauge invariant. And the way it is done is gauge field is traded for what's called gauge links. So our matter fields live on sides of the lattice, as you would imagine scalar or fermion field would do. But the gauge field in its nature, right, it's a gauge covariant transporter between the sides. So if you want to know how to take field on one side and move it to the other side, you have to multiply it by this kind of integral in which rotates a field in the color space. The reason you want to move fields from side to side, you want to calculate the covariant derivative, right? So the covariant derivative will look like this. You have a field in the positive direction multiplied by the gauge link in positive direction minus field in the backward direction multiplied by the field gauge link in the backward direction. And this kind of covariant derivative turns out is gauge covariance, right? So a field transforms, whether it's scalar or fermion, if it transforms with a gauge, some kind of gauge rotation, then the same will happen to the covariant derivative. And the links themselves transform also in a simple way. You just multiply by the gauge transformation on the initial side and the gauge transformation dagger on the final side. And in order to calculate the action of the field, all you have to do is to take the circulation around one plaquette. So this is like U1, U2, U3, U4, and then take the sort of the lowest order and lattice spacing of this. So you can easily see that this action is in fact a product of this. It's a real trace of the product of four links, and this is computationally very easy to do. You don't really need to calculate any of these exponentials, right? So you kind of have the discretization error. Because in principle, this exponential for small lattice spacing and small coupling is, you can expand it into 1 plus order A, right? So you drop 1, but then you have higher order corrections in A. It turns out that in this procedure, this action is precise to order A squared, but you can introduce also a rectangular loop in addition to the square. So it's 1 by 2. With all possible orientations, of course, and tune the coefficients so that the order A squared corrections will cancel, and you have precision order A to the fourth, which is more than you get in fermions anyway. All right, so questions so far? Stop me at any point if you have a question. Okay, so now what about the algorithms? We need to calculate this path integral efficiently. And this, as you have seen, this basically turns into a statistical system, right, with something that looks like a Boltzmann weight. As you know, in a statistical system, in a large volume, the distribution of the energy is very narrow, right? So it's a canonical ensemble in which this energy kind of fluctuates. And the fluctuation width is a order of temperature. It does not go with the volume. So if you try to generate just randomly gauge links, right, as some simple Monte Carlo algorithms do, then you will never get right at this peak of the balance of entropy in the action. Instead, you design a Markov chain based on the Monte Carlo updates. So the idea is that if you have already a gauge configuration which is in this balance, within this balance of entropy and action, then you can design some kind of update which will go to the next candidate, which is as far away, as independent as possible from the original one, but it also stays within this balance. To arrive at this original configuration. You start from, let's say, just all gauge field 0, and then you apply this algorithm, and then there is a theorem about Markov chain that tells you it will converge to this distribution. The typical algorithm to do that is a metropolis update, right? So you construct a candidate which has a reasonable chance of being within this bounds of entropy and action. You calculate the change of action, this delta S between the new and the old, and you accept or reject it with a probability which works as this. If the action is diminished by this update, then you accept it. If the action is increased, then you accept it with the probability exponential in the action change. So this action change has to be of order 1, otherwise it will never be accepted. It turns out this algorithm works very well if it's easy to construct candidates that are close in the action to the current configuration, and if it's easy to calculate the action change. So a typical example is what's called a quenched QCD, in which you do not have dynamical quarks. So it's just this exponential here, right? And then the action has this product of 4 links. And the change in the action you can easily calculate. So there is this 2 staples or 2 d-1 staples in each perpendicular direction, right? And the change is simply linear in this new gauge link. You have to generate the new gauge link in the way that is sort of equally distributed on the Haar measure. So you want to be, you don't want to skew your probability distribution in any way. But after you've generated that, you can evaluate. So you can take just one link, right, and see how much action is changed. And this will be order 1. And then you accept or reject it depending on some random dice roll. And that works what's for local updates, right? What we call local updates. The change in the action is local. If you change just one link for this action, but what to do if you have also fermions? So you can imagine this determinant of the operator, of the differential operator involving the gauge field. It's a covariant differential operator. It will be very non-local, right? So you can try to promote it into the action in this form, but it's still non-local. And in this case, you do what's called molecular dynamics or hybrid Monte Carlo. Essentially, this is similar to Langevin algorithm. And the idea is that you simulate this determinant also by path integral. So you can put it back into the action by converting it to integral over bosonic fields. So you should note there that the action term is the operator inverse, right? So these are the rules of integration, Gaussian integration over bosonic fields. So when you integrate over fermions, you get the operator itself, determinant. If you integrate over bosonic fields, you get the operator inverse determinant. And so now you have this kind of additional path integral that you can do. And the way you do this, you convert your canonical ensemble into a microcanonical, and which is governed by this kind of Hamiltonian. Okay, and you before you start your update, you basically randomly select momentum and the fields which do not have physical meaning. For example, these auxiliary eta fields, you select them according to some Gaussian probability, according to the action. And this Hamiltonian, then you can use to find the equations of motion and integrate them, right? So, and what happens is that when you integrate these equations, the Hamiltonian does not change. Well, at least up to the integration error. And this is how you get precisely to the next candidate without changing the action. So the action now incorporates this full action, including the pseudofermions, and also the kinetic term. For this kinetic term is both for the gauge fields and pseudofermions. So the couple of things to make sure it works is it has to be reversible, right? So if you change the sign of momentum, it has to go back to the original. And there's a finite difference scheme that does that. If you don't do that, the algorithm will not be ergodic. You can imagine that the phase space of these fields will collapse somehow. You don't want to do that. And also because the integration is never precise on the computer, you have some kind of a change in the action, but this is usually small enough and it can be corrected with the Metropolis algorithm the same way as before, but now you have to evaluate the action at the beginning and at the end. So the reason it works is that we calculate observables which depend only on the physical fields, right? So these phi here is just physical fields, no pseudo-fermions, and the integral over the momenta and the auxiliary fields is just trivial. It's just Gaussian. All right, so these are the two algorithms that are used almost in every calculation on the lattice these days. Of course, most of the calculations are currently done with the dynamical fermions, and that's why people have to use that. So just a quick example of what we have on the lattice. We have fields which are sort of large fields, as we call them, right? So there are perturbative fields which are small, and you can expand the path integral in them, but then there are large fields which are topological, and this is an example. So can we, Frank? Can we start the movie?
Yeah.
Oh. How do I do that? Just click on it?
Yeah, I think the batteries are going.
All right, so the blue and the red are the lumps of the topological charge. So these are otherwise known as instantons and anti-instantons, right? And they are particular configurations of fields where electric and magnetic fields are sort of co-aligned or anti-aligned, and that is each of them can be approximated. Well, in classical theory, they're known as the winding number, right? From the color group to the S3 sphere. So these configurations are important, for example, for the theta term, right? So the theta term is a hypothetical term contributing to the QCD, which violates CP symmetry, charge parity, and we don't know if this term exists. So if this theta is 0 or not, and we, for example, try to detect this theta term via the electric dipole moment of a neutron or a nuclei. All right. So each of these instantons basically represents a quantum tunneling between topological sectors, and there is an energy barrier associated with that. And this energy barrier, the height of that actually depends on the lattice spacing. So there is, if you take the full four-dimensional configuration of fields, there is no continuous way to go from one configuration to another. But it's possible on the lattice because the finite lattice spacing sort of cuts off the energy, right? So you can kind of break the continuity in the fields and then generate instantons and anti-instantons. But with the fine lattice spacing, that becomes more and more difficult. If the lattice spacing goes to 0, that energy barrier goes up. All right, so now we have our lattice Lagrangian, right? So we have some kind of discretization of fermions, and we have discretization for the gauge action. We need to set the parameters. There is a strong coupling, which is inverse G squared, and we have work masses, and typical way it's done is, strong coupling is most directly related to the lattice scale or the lattice spacing, right? So there is a running coupling that depends on the UV cutoff, which is lattice spacing is. But then there are also light quark masses. Let's say they are equal because they're close and we just neglect the effect of their difference. And there is a strange quark mass and maybe heavier quarks. But let's, if we limit the quarks only to these three species, then we need to pick three quantities from the physical world. Typically, it's pion mass, kn mass, and one of the baryon masses. And for example, pion mass is most sensitive to the light quark mass. Kn mass is sensitive to the combination of light and strange, right? And the scale is sensitive to, to the strong coupling, right? So we set the scale, the overall scale, by looking at something, some heavy baryon usually, that is easy to calculate, have few corrections from light quark masses. And then we deduce the overall scale just from the ratio of lattice mass to physical mass. Right? Questions? So if we have additional quarks, so more recently, lattice calculations started incorporating the charm quark. So we would take another baryon from that, from the spectrum. All right, so of course it gets very expensive if you try to do realistic calculations. And there are two kinds of challenges, broadly speaking. There are challenges that you can overcome with a brute force. So modern lattice size in sites can be 64 sites in space and 128 in time. And if you want to go closer to the continuum limit, sort of below 0.05 Fermi, then you have to go even higher site count. And you also want to keep your volume large enough so that's approximately what it combines to. So it's about 5 Fermi and, well, maybe 4 Fermi and something like 0.06 Fermi lattice spacing, right? 5 Fermi box, 4 Fermi box, something like that. And it's just the sheer volume and the memory size required to store gauge configuration is large. You can fit it only on a cluster. And another reason it's get expensive, there are light quark Dirac operator inversions are expensive. So they are fully determined operators, and there are algorithms based on the multigrid algorithms that do this efficiently on the distributed computer clusters. And you have to do this for two reasons. You have to do this for the evolution of the fields themselves, as just discussed. And also you have to do this for quark propagators to calculate observable, such as correlators. Another challenge is that there's just Monte Carlo statistical noise, especially if you calculate something like a gluonic density or energy momentum tensor due to gluons inside a hadron that is fluctuating wildly, and you have to generate order of 100,000 or million samples to get deep down on uncertainties. And for a while, for this reason, calculations were done in smaller volume and larger, heavier pion mass. So these were all, it's a scatter plot of the pion mass. Physical is this horizontal line and lattice spacing, right? So many calculations were done with coarse lattice spacings and heavy pion masses. And eventually, with time, we got to this physical sort of pion mass. And we keep pushing towards the continuum limit. Most of the calculations are done between 0.05 and 0.10 Fermi lattice spacings. You have to do this on a large machine, but even with that, there are tough challenges which are hard to overcome. So there's so-called critical slowing down, and it turns out that it's just difficult to explore the entire space of the gauge field configurations. One particular reason for that is that there is this topology. So the finer lattice you have, the more difficult it is to transition between different number of instantons. Yeah, because in continuum limit, the topological sector would be infinitely high. On the lattice, it's finite, but gets higher towards the continuum limit. So basically, you have the topological winding number freezing, and that is non-ergodic, and also it can introduce CP violation. So the solutions to that were currently developed. It's a multi-scale evolution where you sort of evolve the field on the coarse lattice and then promote it to finer lattice. And they have some matching between fine and coarse lattices based on some machine learning. Another problem is if you try to introduce a chemical potential for baryons, kind of breaks the symmetry between quarks and antiquarks, right? And in this case, you have a complex fermion determinant. This complex fermion determinant, if you remember this statistical weight that has exponential of the gluon action and determinant, so that if that becomes complex, you have a sign problem, right? So not only complex, it becomes negative. So the problem is very bad because the fluctuation of this determinant becomes worse with the physical volume. And you cannot really overcome this with statistics because it's just exponential in volume. And for this reason, it's very difficult on the lattice to do equation of state. So if you have non-zero chemical potential, or non-zero baryon density, right? It becomes a very hard problem. And currently, people work hard inventing algorithms for quantum computers. So who knows, maybe it's a future. We build quantum computer comparable to this size. So it'll take maybe a few decades. All right, so now let's go to the actual observable calculation. I'm already over an hour, right? I'll try to speed up. So how do we calculate anything useful from lattice? So one thing, for example, is the masses of hadrons, right? So let's take the simplest example of pions. And basically, since the fields and their correlators fall off exponentially with the energies, if we put creation operator and its conjugate some space apart or time apart, right, we can just calculate the contractions, the weak contractions of the fields. And that is one of the most, the simplest calculations to do on a lattice. So you basically have a square of the propagator. And since there are no cancellations in this trace, everything comes with a positive sign. Pion is the lightest particle, right? So the correlator of the propagator squared will be large enough distance, it will overwhelm any other correlator. You can write any kind of quadratic expression, quadratic work propagator. And on lattice, it looks like, so you have a creation operator, annihilation operator, and you can track the quarks. So these lines are basically just T/inverse. If you have a nucleon, it's the same thing. You do all weak contractions. You have two diagrams, right? Because of the permutation of quarks, you have a minus sign, right? So two U quarks flip, we generate a minus sign, which is typically compensated by the color antisymmetry of them. All right, so that is just the 2-point function. And so the way we interpret that 2-point function is we separate them in time, and you can insert a complete set of states between creation annihilation operator. And by the way, there is a somewhat interesting caveat here. So this spectral expansion relies on the existence of the transfer matrix. Transfer matrix is the operator, quantum operator that connects the time slices, sort of a progression in time in Euclidean space or in statistical mechanics. And it's been proven that it exists only for some actions, not all of them. For example, if you incorporate corrections like Clover term, I don't think it's been proven to be for the transfer matrix to exist. In some other cases, so it's still kind of taken on faith. It works usually. So you have the sum of exponentials, right, where you have the ground state, the actual physical pion, and then there are all excited states of that with the same quantum numbers. So you have to sum of them over all of them. But at the long enough time separation, only the ground state pion, the lowest energy, survives. And in order to estimate that, we write something like that. So it's a logarithm of just a sort of logarithmic derivative of the pion correlator in time. And then you plot it as a function of this time, and it converges to a plateau. Right. So actually, this picture is for the nucleon for different momenta. And as you see, there is usually a plateau somewhere if you wait long enough in Euclidean time. All right. So now if we have something else in mind, for example, if we want to calculate the matrix element of the vector current, if we want to study the charge distribution inside a pion, we would insert this U bar gamma mu U somewhere in between, right? And do the same thing with the weak contractions. Now we have a spectral decomposition in which we have the matrix element in the middle. Again, taking the large time limit, all the separations between the operators have to become large. We have the dominant contribution from the ground state. And this matrix element is usually extracted from the correlators. For example, if you're just interested in the forward limit, you can divide the 3-point function by the 2-point function and plot it again as a function of the separations between operators. And eventually, as the separation increases, that kind of converges to the ground state. But the more practical way to do this is to, of course, to do fits, right? So the 2-point function is just the sum of exponentials. So we would do a fit And we can even pick out excited states. So this is a plot of the energies from fits for the pion with the varying momenta. So momentum goes from 0 all the way to 2 GeV. You have the ground state, which if you look at this curve, it becomes flat, right? So it's a good indication we have good discretization with the dispersion relation the way it should work. And then we can even pick out the first excited state. But after that, of course, becomes very kind of noisy. And this is sort of sometimes called the garbage bin parameter, which collects all the higher energy states. If you want to if you do the same to the 3-point correlator between pions and some insertion, so in this case, it's vector currents, you kind of do the same, but you're limited on how many states you can include because this is 2 states and 4 matrix elements. 3 states would be 9 matrix elements. So you have to introduce some constraints. And I have to say that these excited states are probably the hardest systematic to control in current calculations, especially when this energy gap becomes small, right? And it's quite clear why. If you have the energy gap collapsing, typical example, if you calculate something for the nucleon, but the excited state, allowed excited state is nucleon pion. For example, that happens in the axial charge that I mentioned. And this just fit is poorly determined, right? So with a small energy gap, it's just difficult to do a fit. And pion in this case is very easy to work with because the energy gap with the water is larger than the state itself. So we have been able in this work to extend the source sinks operation to like this is basically 2 Fermi or more. And that gave us, for example, good results for the high momentum form factor of the pion. All right, so just a word on how to connect lattice calculations to other theory. So you have to, for example, if you calculate, let's say, quark momentum fraction of the lattice, it has non-trivial scale dependence, right? So, and as you change the lattice spacing, the scale changes, means you'll get a different number for each lattice spacing. You have to connect it to something like MS bar. And the way to do this is to renormalize either using lattice perturbation theory that was done quite early, and it's very cumbersome. You can imagine you have to expand in these lattice fields and deal with the lattice propagators. And also, in the end, you will be limited by the order of perturbation theory quite quickly. You cannot go to small lattice spacings with that, right? Because coupling becomes large, the convergence becomes poor. So what's almost universally used is what's called regulator independent scheme, momentum sort of shell subtraction, where you essentially do the same as you would do momentum scheme and continuum. You put the plane wave quarks on the lattice, quark fields, right? And you calculate the correlator between the operator and these plane wave quarks, which have fixed 4-dimensional momentum. They're off shell. They are sort of highly virtual, right? So they couple only at short distance. And then you determine your lattice renormalization constant, just comparing to the tree value of that. And so this is fairly straightforward to calculate. The only thing you have to do is to do the gauge fixing. So if you don't do gauge fixing, it just will average to 0 because these quarks carry color indices. And then you compare the lattice renormalization factor to the same from perturbation theory, for example, MS bar, and you take a window of scales somewhere between maybe 2 and 5 GeV, and it's called a matching window. You want to be as far away as possible from the lambda QCD, right, from the non-perturbative scale, and also you want to be far away from the discretization scale on the other end. And another comment here, so this is an example of what you get. So it's, by the way, done with the chiral fermions. And the way you see this, the axial and vector renormalization constants are basically on top of each other. There is no difference in the renormalization of the axial current and the vector current. But the scalar operator and pseudoscalar operator have a problem because if you have 0 momentum at this point, it will couple to the pion, right? So it will basically couple to the chiral condensate on the lattice. And this will diverge as, for example, if it will get a large contribution of a pion pole to this vertex. So the way you get around this is you introduce the momentum at the vertex itself, and then it kind of lifts the pole, and then this dependence will disappear. All right. Okay, so to finish today's talk, I just want to go over the systematic effects. So I already mentioned all of them essentially, but what do we do with them? We, in the end, have to do calculations with multiple lattice spacings, lattice volumes, and the pion masses. And well, the pion mass maybe not, because most of the recent calculations are done exactly at the physical point. So discretization effects are usually everything is done with a good discretization. So you only have like a squared corrections, right? So if you have some range of spacings, let's say between 0.07 and 0.10 Fermi, then you can just do a fit, assume that you only have a squared correction, and extract the continuum value. The finite volume effects, the reason we want to keep the box large enough is that this term is small and there are no higher terms like 2 pion, not exponential of minus 2m pi-l, which decayed already. So again, using 2 or more volumes of lattice, we can do a finite infinite volume extrapolation and extract the infinite volume value. So for some quantities, you actually want to do a calculation at the unphysical pion, just because it's cheaper and you need enormous statistics for that particular observable. And if that's your way of doing things, then you can just use Karl perturbation theory, which behaves something like that. That's just an example. It's a good example where you have well-defined Karl limit value, right? And then you extrapolate it to the physical point. Not all the quantities behave like that. So there are quantities which are divergent in the Karl limit. And one of the examples is the proton radius. So if you calculate proton radius with decreasing pion mass, you will basically see like a logarithmic pole. And also, the closer you get to the continuum limit or physical point, the sharper the dependence is. So only recently, the proton radius has been calculated at the physical point. And the most important systematics is the excited state effects. So this is probably the most concerning one, many calculations. And the way to do this is to just beat it down with statistics to have well-controlled multi-state fits, constrained multi-state fits, or you can do variational analysis with a basis of creation and annihilation operators. So that linear combination would give you something that is closer to the physical state. All right, so that is all for today, and we will continue tomorrow. Well, this afternoon I should be working on the second half.
Anyway, so yeah, let's save the questions for later. And well, again, yeah, he's on this for us. We can find him there. So yeah, but let's take the full time. We'll start at 1:30.